Alright, hello everyone. I hope you guys are doing good. So today I'll be discussing the solutions to Atcoder Beginner Contest 228. This contest was held earlier today. And again, talking about the difficulty, I would say this one was like a really balanced round. The round was well balanced and the problems were actually beginner friendly. So any beginner can like solve the first 4 problems if like he has some experience. So yeah, I would say that this one was a very well curated round. It was unlike the past 2 or 3 Atcoder beginner contests, which were like kind of unbalanced. So yeah, this one was a really nice round. So yeah, let's jump right into it and start with the solution to problem A. Also, I will be discussing the first 5 problems from A to E. Okay, let's see. So this one is a really easy problem. What we have here is there is a clock which is turned on at S o'clock every day and it is turned off at T o'clock every day. And we have been given with a time X and we need to determine whether the clock is on or off at X past 30 seconds, right? So instead of the clock, we have a light. Actually, the light is turned on at S o'clock and it is turned off at T o'clock. And we need to determine whether the light is on or off at time is equals to X plus 30 hours. Right, this is all the information given to us and it will be better to understand the solution through the code. So really what we have here is we have 2 cases. The first case is when the clock is turned off during the same day, that is t is greater than s. So if t is greater than s, then any time which is smaller than s, the light will obviously be off. But any time which is greater than or equals to s but is less than t, the light will be on. And after the time is t, then the light will be off. Similarly, the second case is when the light is turned on one day and it is turned off on the other day, and that will happen when t is less than s. So if t is less than s, then any time after s is obviously the light will obviously be on because I am turning it off the next day. So if x is greater than or equals to s, then the answer will be yes. And also, if the light has not yet been turned off the next day, that is x is less than t, the answer would still be yes. But any time between t and s, the answer will be no. So these are a few cases in this problem. I'm sure there are easier implementations and smaller implementations, but this one just makes it really easy to understand. So yeah, I have made all these cases. So this is really all that the first problem wanted from us. So that completes its solution. So let's move on to the second problem. Alright, so here Takahashi has n friends and they have nicknames friend 1 up to friend n. And one day Takahashi accidentally let one of his friends, let's say the ex friend, learn his shameful secret. And for each I from 1 to n, if friend I learns the secret, he or she will obviously share it with another friend, that is his best friend. And the best friend of friend I is a of I. So if the friend I learns the secret, he will immediately share it with his or her best friend, which is a of I. And that will happen if and only if a of I has not already learned it, obviously. And finally, we need to tell that if Takahashi tells his secret to friend number X, then at the end of the day, when everyone has told the secret to their best friends, what will be the total number of people who know Takahashi's secret, right? So yeah, this is the problem here. And again, it is not very difficult to think. Obviously, there are better implementations and better methods to solve it. But what I will do here is that I'm going to model this as a graph problem. So for every friend I will take that as a node in my graph and it has an edge. The friend I has an edge to a of I. That means if the friend I learns the secret, he will tell it to the friend a of I. So what we can do here is that we can start from the friend X and just carry on and just make a DFS in the graph. And finally, all the nodes which have been visited in the DFS are the friends who will know of Takahashi's secret. And all the nodes which haven't been visited are the friends which will never know his secret. So at the end of the day, I will just count the number of visited nodes if I start a DFS from the friend X. And when the DFS is over, the count of the number of nodes which have been visited will be my answer. Another method to do this is to notice that there are only n unique friends. So the total number of unique friends can never exceed n. And what I can do is I can just keep going from I to a of I, then from a of I to a of I, then to a of I, and so on, up till a maximum of n times. because once I have gone to a maximum of n people, it can never exceed because the total number of people here is n. So after about n operations, I will just break out of my loop and just tell which are the people who have been visited yet. So that's another method, but the better implementation will be the one with DFS. So let's just have a look at the code. So what I do here is that I create a directed graph where there is an edge from the node I to the node A of I, and I will just do a DFS from X, which is standard, pretty standard. So if you don't know about what a DFS traversal of a graph is, you should really learn it because it's really helpful in competitive programming. Again, I just mark the node visited and carry out a DFS to its adjacent node. This vector of adjacency will just contain one node. And finally, I will just count the number of nodes which were visited and increment my answer. So yeah, that's it for problem B. Let's now move on to the next problem. Okay, so this is an interesting one. So here there are n students who are taking a 4-day exam, and there is a 300 marks test on each day. So they are basically fighting for 1200 marks, which are distributed into sets of 300 marks each day. And we have been provided with the marks of the first 3 days for all the children. So for all the students from 1 to n, we know the number of marks that the ith student got on the jth day, where j is from 1 to 3, but we have no idea how many marks the student scored on the last day. So for each student, what we have to do is we have to determine whether it is possible that he or she is ranked among the top k students after the 4th day is completed. Right. So the question is asking us that we have been provided with the data about the marks scored by each student in the first 3 days, but we have no idea about the marks scored by any student in the last day. And what we need to do is for each student, we need to determine that in the best case scenario, is it possible that the particular student is ranked in the top k people or not? That's the only thing we have to tell. And again, the rank is defined as 1 plus the total number of people who scored strictly higher than us. So our rank will be 1 plus the number of people who scored strictly higher than us. And the constraints here are standard. N is up to 10 to the 5 and k is less than n. And obviously the value of Pij is from 0 to 300, since every day the maximum marks is 300. Okay, let's look at the solution. Try to make some observations. So the first thing to notice here is that the entire thing which they have given us in the input, that is P11, P12, P13, the marks of all 3 days separately given to us is just a useless thing. What really matters is the marks scored by the students in all the 3 days. So what really matters is the sum of marks scored by a student in the first 3 days. It is basically useless to consider each day separately, right? So the first observation is that what really matters for each student is Pi1 plus Pi2 plus Pi3. So let's say that sum of I is equals to Pi1 plus Pi2 plus Pi3, because obviously we don't have to do anything with the separate marks scored by every student in every day. What really matters here is the sum of marks scored by every student in the 3rd day. Now the second thing which I'm going to do is I'm going to make a greedy strategy here, and that is because I want to consider the best case. Right, the problem asks us to determine for each student whether it is possible or not that he or she ranked in the top k after the 4th day. So we need to consider the best case scenario. Right, and when we consider the best case scenario, the best thing to improve our rank is that we perform good and all the others perform bad. Right, so if I want to improve my rank, obviously I would prefer that I perform good and all of my competitors perform bad. So for that, what we can do is that the greedy strategy here can be I scored 300 points on the 4th day and everyone else scores a 0. and that is the only way my rank will be improved as much as possible, right? I can't do anything about the marks scored by me in the first 3 days, but what is in my hands is the marks scored by me in the last day. So that is why the greedy strategy that I'm going to follow here is that I will score 300 points on the 4th day and I will let all the others score 0 points. Alright, so now let's say I am considering the ith student, and the marks scored by ith student after 4 days, that will be sum of I plus 300, and that is because the sum of I is already there and I'm considering that he scores full marks on the last day. Obviously, when I will consider the other students, then I will consider that case separately. Both of these cases are disjoint. So in that case, I will consider that the ith student has scored sum of I only, but the jth student has scored sum of j plus 300. So all these cases are separate. Right now, I am assuming that the ith student has scored sum of I plus 300 and all the other students have scored a 0. Then the problem reduces to finding out the number of people, the number of students j, where j is obviously not equals to I, such that sum of j is strictly greater than sum of I plus 300. Why? Because I need to calculate my rank, and my rank is going to be 1 plus the number of people who scored strictly greater than me, and my score is sum of I plus 300, and for all the other j's which are not equal to I, the score is the score is just sum of j. So I want to find the number of j's such that sum of j is greater than sum of I plus 300, and let's say that number is x, then my rank will be 1 plus x. And once I have determined my best case rank, I can just say that if my best case rank is less than or equal to k, then the answer would be yes, otherwise the answer would be no. Okay, and obviously once I have figured out this logic, it is very easy to find this number. We can just sort the sum array and do a binary search to figure out the number of people who are scoring strictly greater than 300 marks. That is a really easy thing to do. So yeah, this concludes the solution. I can just sort the sum vector and find out the total number of people who have sum greater than sum of I plus 300, and that can be done using upper bound, and just figure out that if that number plus 1 is less than or equals to k or not. If that is the case, then the answer would be yes, otherwise it would be no. So that is it for problem C. Let's just have a quick look at the code. So I'm creating this sum vector which is storing the sum of all the marks scored in the first 3 days, and it is also keeping track of the index, and then I'm sorting this vector. And finally what I'm doing is I'm finding the total number of people who have scored strictly greater than me, and I can do that by finding the number of people who have scored less than or equal to me, which is stored in this number small, and then subtracting n by small. And so my final rank is going to be n minus small, where small is the upper bound for my score plus 300, and then my rank can be calculated as n minus small. Right. So to elaborate on this, what I'm doing here is that this small right now stores the number of people who have scored less than or equal to me, but that also includes me, right? So that is why I'm doing small minus equals to 2. The small minus equals to 1 is done because this upper bound is calculating the required value plus 1. So obviously I have to decrease it by 1. But even then, this small will contain me, and I don't want myself to be included. So I am decreasing small by 2. And then my rank will be just n minus small. And if my rank is less than or equals to k, then my answer will be 1. Otherwise, my answer will be 0, where 1 denotes a yes and 0 denotes a no. Right, so this is how we approach problem C. That is it for this problem. Now, let's move on to the next one. Okay, so this problem is called linear probing, and again this is a very interesting problem. If you are not able to solve this problem, then be ready, because you are about to learn something which is going to be very helpful for you, because this is something which we use very frequently in competitive programming. The concept used in this problem is a very frequent concept in competitive programming. So yeah, let's see what this problem has to say. So we have a sequence of n numbers starting from a0 to an minus 1, where n is equals to 2 raised to the power 20. And 2 raised to the power 20 is roughly around 10 raised to the power 6. And initially, the every term of the sequence is just minus 1. And what we have to do is we have to process q queries, and all the queries have to be processed in order. So a query is denoted by two numbers, ti and xi. And if ti is equals to 2, then we simply have to print the element which is at the xi mod nth position in my array. Since xi can be up to 10 to the 18, first I take xi modulo n, and then I check what is the element at the position xi modulo n in my sequence and simply output it. So that's the second operation, which is really easy. But in the first type of query, what I have to do is that the first step is to define an integer h, where h is equals to xi, and then what you have to do is you have to you will first check if a of h mod n is equals to minus 1 or not. If a of h mod n is equals to minus 1, you will just replace a of h mod n with xi, right? But if a of h mod n is not equals to minus 1, you will keep going right. You will start from h mod n and you will keep going right, and you won't stop. Even if you end the sequence, you are going cyclically, so you will keep going cyclically to the right. And once you find out a minus 1, then you have to stop there and replace that index with xi, and you are guaranteed to find a minus 1, because to start with we are having 10 raised to the power 6 minus 1, then the number of queries is just 2 into 10 raised to the power 5. So even if every query is of type 1, even then we will have we will remove only 2 into 10 raised to the power 5 minus 1s, but we had around 10 raised to the power 6 minus 1s to begin with. So we can be sure that we will always find a minus 1 if we move cyclically. Right. So let me just reiterate. In the first query, what we are doing is we are starting at the index h mod n, where h is equals to xi, and then we just keep going right cyclically until and unless we find a minus 1. As soon as we find a minus 1, we are stopping, and if we stop at index j, then we mark a of j as x of I. Great. So this is the problem. One very easy solution here is to just do it naively. And the time complexity of that solution obviously is O of n into q, which is too slow. So obviously we cannot do that. Let's look at a better solution then. Let me just make sure I'm recording. Yeah. Okay, so let's look at a better solution then. Problem D. So in the query of first type, what we are doing is, so let's write down formally what we actually want. We start from h is equals to xi mod n and keep going right cyclically until we find a minus 1. And if we find minus 1 at index j, then we replace a of j with, so if we find minus 1 at index j, then what we do is we replace a of j with xi. Okay, so in a sense what we want to do is we need to find the smallest j greater than or equals to h such that a of j is equals to minus 1, right? Because we are starting from j and we are going right. But another sub case here is that if there is no such j greater than or equals to I such that a of j is equals to minus 1, then we are sure that there will be one index which is less than I, which will be minus 1. Because again, the number of queries is 2 into 10 raised to the power 5, but the number of minus 1s initially that we had is a lot. So we will have at least one minus 1. So it will either be towards the right or towards the left, or both to the right or to the left. But if we don't find a minus 1 to the right, then obviously it will be a minus 1 on the left. And what we want is that if there is no such j to the right of I such that a of j is equals to minus 1, then we just need to find the first minus 1 in the sequence. Because we are going cyclically, so if we finish the sequence and don't find a minus 1, we are going to start from the beginning. So we will want to find the first index of the minus 1. Alright, So yeah, formally this is what we want. So this is the case 1 when we have index j such that a of j is equals to -1 to the right of h, and that will almost always happen. Very rarely it will not happen, and in that case we just have to take the index of the first -1 in the sequence. Okay, so this is not a very rare situation. If you are experienced in comparative programming, it is highly probable that you have faced such a situation before. In such situations, what we want is we want to find the index of the first place where something is happening. So what we do in such situations is we keep a set, and in the set we keep only the positions where the particular situation that we want is happening, right? And in this case what we want is the indexes of -1s. So what we are going to do is we are going to keep a set in which we will maintain the positions of all the elements, the positions of all the indexes where there will be -1. So we take a set and maintain in it all indices I such that a of I is equals to -1. We need to make sure that if an index is in our set, then a of I is always -1. If an index I is in my set, then I need to make sure that a of I is equals to -1. And if I can successfully do that, let's see how that is helping me. So if now I have a set such that for any index I, if it is in my set, then a of I is equals to -1. Then what I want here is I want to calculate the first index which is greater than or equals to h such that a of j is equals to -1. And that will be the first index greater than or equals to h in my set, because all the -1s are in my set. And so that can easily be found using lower bound, right? But if we do a lower bound and if we don't find any such index, then that just means we have to take the first j, which is the first index in the sequence, which is -1, which will obviously be at the beginning of our set, and that can easily be found out using set.begin. So it will either be the lower bound in our set of h, and if that doesn't exist, if the lower bound doesn't exist, then we will just take set.begin, because that will be the first index of the sequence, which is -1, right? So using this set we can optimize our approach, and we will find this index in logarithmic time. And once we have found the index, we will just mark its value and replace the -1 with x of I. And once we do that, we have to make sure that we erase the element from the set, because if we don't do that, then our set won't be maintained. We only need to maintain those elements which are not -1, right? So yeah, this is the solution, and this is a very important concept which you need to remember, because it comes in handy very often in competitive programming. So yeah, that was the solution to problem D. Let's just have a look at the code once. The code is pretty short and concise. So what I'm doing is I'm taking a set, and I'm also keeping a sequence of length 10 to raised power 20. Initially everything is -1, so I am inserting every index I from 0 to n-1 in my set. And then in case 2, I am simply outputting the element at the position x mod n. But in case 1, what is happening is I am first finding the lower bound. It is storing the lower bound of x. But if it is st.end, and that means that the lower bound doesn't exist, then it will just be st.begin, because then it will be the first index of my sequence, which will be -1. And after that, I can simply do I can simply change the position I can simply change the value of the element which is at the position *it to be x1, where x1 is just equals to x, and that can be accessed through *it. And then I have to make sure that I delete this iterator it from my set, because that way I am maintaining in my set only those indices which are -1s, right? I hope I was able to explain it well enough, because this is a really important concept. And yes, this concludes the solution to problem D. So now let's just move on to the next and the last problem that we'll be discussing today. This is problem E. Okay, so let's see what this problem is trying to tell us. So integer sequence exhibition is taking place, where integer sequences are gathered in one place and evaluated. Here every integer sequence of length n consisting of integers between 1 to k is evaluated and given an integer score between 1 and m. So what we need to do is we need to print modulo this big prime number, the number of ways of giving each of the evaluated sequences a score between 1 and m. So in a sense, we have n sequences, and what we have is we have sequences of length n, which consists of elements from 1 to k, and we are taking all such sequences, any possible sequence which is of length n and it contains elements between 1 to k, and then we are assigning them a value which is from 1 to m. So we have to find out the total number of ways to do this. And the thing to note here is that the constraints are really huge, and that is the main thing which is difficult in this problem. Otherwise, this problem is really easy. Coming up with a solution and coming up the expression for the solution is like really easy here. But still, let's see how we can come up with the solution. And let's notice how to solve the problem for this simple test case of n is equals to m is equals to k is equals to 2. So as you can see, for any sequence of size 2, if all the elements are from 1 to 2, then we really have two choices for every element. And since we have n elements, then the total number of sequences will just be 2 into 2, which is 2 raised to the power 2. And as you can see here, there are 4 such sequences. Now, to each sequence, you can assign any value from 1 to m. And so, for each of these 4 sequences, again, you have two choices, either to assign it a score of 1 or to assign it a score of 2. So, your final answer would just become 2 raised to the power the number of sequences, because for every sequence, you have two choices. And so, it becomes 2 raised to the power 4, which is 16. And to write it formally, what we have is, so first we will calculate the number of sequences. So number of sequences can be easily calculated because the length of every sequence has to be n, and every element can be from 1 to k. So really we have like n places, and for every place we have k choices. So the number of sequences is simply k raised to the power n. And now for each sequence we have m choices to assign it a score from 1, 2, 3 up till m. So what we have is k raised to the power n sequences and m choices for each sequence. So the total number of assignments, total number of ways then becomes m raised to the power the number of sequences, because for each sequence we have m choices. And so our final answer just becomes m raised to the power k raised to the power n. And we need to find this value modulo p, where p is equals to this number given to us. And obviously this is again a very standard number, and we know for sure that this is a prime number. Right. So one would argue that we can just do a binary exponentiation and do something like this: m raised to the power. So we can do something like this. Take m and then raise it to the power k raised to the power n modulo p, then again take modulo p. Right? This is something that seems very tempting, that someone would want to do when they are trying to solve this problem and just get away with it. But it turns out that the relation a raised to the power b raised to the power c modulo p is not equals to a raised to the power b raised to the power c modulo p, right? So you can't just take the modulus of b raised to the power p by b raised to the power c by p and then just raise that to the power of a modulo p. So that is something you cannot do. So in a sense, what I'm trying to say is that this problem is not very simple. So let's see how to solve this. And to solve this problem, the first observation to make is to use a theorem, which is again not a very well-known theorem, but again it is a very famous theorem, which is called Fermat's little theorem. So now we are going to talk about Fermat's little theorem. So let's say we have a number a and a prime number p. Then Fermat's little theorem says that for a number a and a prime p, one thing that always holds, a property that always holds, is that the remainder when a raised to the power p minus 1 is divided by p. So a raised to the power p minus 1 modulo p is always equals to 1. So this is what Fermat's little theorem says. And again, when we calculate modular inverses, again this theorem is very useful because we know that the modular inverse of any number a is just a raised to the power p minus 2 modulo any prime, and that relation always comes using Fermat's little theorem only. Okay, so now we know this. So let's tackle what we want. So our final answer here is m raised to the power k raised to the power n modulo p. Okay, let's say that k raised to the power n is equals to some number x, right? So then our final answer becomes m raised to the power x modulo p. Okay, so let's take k raised to the power n to be x. And now what we'll do is, again this is something which is well established and that is why I'm doing this. But I can't tell you how to actually come up with this, because this is a standard thing and people have come up with this, right? So yeah, what we are going to do now is let x be. So what we are going to do is we are going to divide x with p minus 1, and then if we do that we will get a quotient and a remainder, right? So let's just say that if we divide x with p minus 1, the quotient that we get is q and the remainder that we get is r. And that way x can be written as quotient times p minus 1 plus remainder, right? So now let's replace x with this value. So what we will be left with is m raised to the power q times p minus 1 plus r modulo p. Right. So this can also be written as m raised to the power q raised to the power p minus 1 multiplied by m raised to the power r and taking whole modulo p. Okay. Now again this can also be written, this first term m raised to the power q raised to the power p minus 1 can also be written as m raised to the power p minus 1 raised to the power q. That is allowed. So this can be written as m raised to the power p minus 1 m raised to the power p minus 1 raised to the power q. And this second term will just stay as it is, m raised to the power r, and then we have to take this whole modulo p. Alright, so now what we can do here is that we can again break down this first term into m raised to the power p minus 1 modulo p raised to the power q, right? And what we realize from Fermat's little theorem is that m raised to the power p minus 1 modulo p is just going to be 1. So if we are taking this whole term modulo p, then what we will be left with is, so since m raised to the power p minus 1 modulo p is equals to 1, what we are left with is 1 raised to the power q multiplied by m raised to the power r modulo p, and this is nothing but m raised to the power r modulo p. And now this has been broken down into a very well known expression which can easily be calculated using binary exponentiation. Here m is just given to us in the problem and r is remainder when k raised to the power n is divided by p minus 1. And again, in a sense, r is equals to k raised to the power n modulo p minus 1, and this expression can again be evaluated using binary exponentiation. So in a sense, we will be required to do two binary exponentiations. First, to calculate this value, where p minus this value k raised to the power n divided by p minus 1, which can be calculated using binary exponentiation. Then a second exponentiation to calculate m raised to the power r modulo p. Right? So yeah, this was the solution to problem E. Let's just have a look at the code now. The code is pretty short and concise. So I already have a built-in power function, a built-in binary exponentiation function. Let's just have a look at that. So this power function calculates the a raised to the power b modulo mod, and this is a pretty standard binary exponentiation. If you don't know about binary exponentiation, again, you should learn it. It is really useful. So first of all, what I'm calculating is I'm calculating b raised to the power c modulo m minus 1, modulo mod minus 1. Here mod is just prime, mod is just the big prime number which is given to us in the problem. And then what I'm doing is I am calculating the power of a raised to my previous answer, which is nothing but r, right? And then there are a few corner cases here. One is that if b is equals to 0 and c is not equals to 0, then obviously answer would be 1. And the second case is that if a modulo mod is equal to 0, then obviously a raised to the power anything will just give 0 modulo mod, right? So then the answer would be 0. Otherwise, the answer would just remain same, and I can simply output that. So yeah, this was it for problem E, and that concludes my discussion today. So I hope you were able to solve one or two problems which you were not during the contest. So that is it from my side today, and I'll see you in the next video. Bye bye.